So from general, there was a bit of motivation about what is StatMech and so on, and then we defined what is the workhouse of phase transition in StatMech, the icing model, which was a collection of spins on any chosen lattice. It could be square lattice, cubic lattice, triangular lattice, the lattice of your choice. And at each lattice side, there's a spin which can point either up or down. So we call plus minus 1. And there's a minimal interaction that is added, that neighboring spins on neighboring sides can interact, and if they are aligned, energy is lowered. So that was the model. And this simple model, using a mean field analysis which replaced the interacting spins with the effective one particle spin model. Even that simple model, we could show that there is a phase transition in this icing model from a low temperature phase where the spins are aligned to a high temperature phase where the spins are disordered. Okay? And that disorder is captured by magnetization, which is the sum over all spins. So it is non-zero here and 0 here. Also, there was some critical point that was identified. At that point, all the thermodynamic quantities like magnetization, susceptibility, or this specific heat, they all became singular. Singular meaning non-analytic, and that non-analytic behavior is captured by critical exponents, same notation beta, gamma, and so on. Okay, and within the mean field, these were computed, and then I made a remark that these are not the actual answers. Okay. Now, today we will I will try to tell how.
I had a question. In the last lecture, you mentioned that like once we have multiple solutions of then like you find out which is the correct, we cannot use stability analysis because the like stability one may not be the but when doing stability analysis, isn't there one method to find stable states by constructing a potential like and we look at states and we consume that those are the stable.
So that the free energy is like some potential like that.
So why shouldn't the stable? So why are they both not equivalent?
Why are they not? That I am telling just from experience.
But could you explain?
Because there is no bigger principle involved in stability. The principle involved is minimization of free energy. That is all. I think that is that. Why should a stable solution minimize free energy? I do not know.
But isn't the stable solution derived using the?
No, the solution, the m star came from a solution of some self-consistent equation. Now, if I were to take that equation and do some temporal evolution, it may go to some m star. But that does not necessarily mean that will minimize your free energy. That is the point. Sometimes it doesn't, sometimes it does. So, now if I give you a generic system, which could be icing model, which is like system in equilibrium, or a generic non-equilibrium model, you would like to know how can I put it on a computer and solve. Okay, so the standard technique is something called Monte Carlo simulations, which I will tell how one does for a generic system. I'll discuss. That will be quite useful. Then in the end, if I get time or next class, I'll discuss how to do it for icing model in particular. So now, why is this not? So we started with icing model. When I specified icing model, what I gave is, given a spin configuration, what is the energy? I didn't specify any dynamics, but only a Hamiltonian. And then there was a recipe for calculation. It said that if I give you, if a configuration C has energy E, then Boltzmann statistics gives you the, or Boltzmann's prescription tells you how to compute the probability of a configuration, theoretically. So on a computer, what is your aim? On a computer, your aim is, I want to generate configurations C1, C2, C3, C4 in time sequence, and they should all appear with this probability. Each configuration different probability. So if I could run a computer simulation in which these configurations are generated, but they are generated not equally, but according to this probability. Then all I have to do is sum over all the, so each configuration I measure an observable, for example magnetization, I sum over them and divide by T, and I can measure all observables like that. So the aim is to generate configurations according to the equilibrium weights. So this is one motivation for our simulations should satisfy this criteria. More generally, not all models are defined through Hamiltonian like Ising model. Sometimes you define a model through dynamics. So which is for example in let us say games, there are agents, they do some decision making on their own, but when they interact with another person, then they change their decision. Now there is no Hamiltonian governing this dynamics. It says that you make some rules. Oh, these two meet, then with probability they will align, with probability and some other probability they will misalign, or some rule like that. Or if I take a random walker, I will say it moves to the left with probability half, to the right with probability half, but that's the dynamics. Then I can make it more complicated. I have many random walkers, they move around, when they meet each other they repel. So they are all defined through the dynamics, but not through Hamiltonian. Okay. So the simplest and most common dynamics is what I'll call Markovian. It means that there will be some rules of evolution, but the rules of evolution depends only on the current state, not on a long time memory. Okay. You can maybe that is not the correct model for some specific system, but this is the simplest system to study. The time evolution in the future depends only on the present and not on the past. Okay. So Markovian. Generic memory, if I have a finite memory, one should not think that this is a specific, what's the word for that, a big constraint, because suppose I say my evolution depends on the current time step and the previous time step. So there is a memory there, but now if I take my state to be a bit bigger and say this, my new state is a combination of the current state and the previous step. Now it becomes Markovian again. So any system with a finite memory can be rewritten as a Markovian system. Only if the memory is infinity, then it goes out of this class. Okay. Is that point clear?
Can you repeat this argument again? Like if you have some very finite memory, then
if I have two-step memory, then I say, oh, now when I define my configuration, I define the configuration in large space, which is the configuration of this time and the configuration of the previous time. So now if I consider the evolution of this combination, it is Markovian again.
But your configuration space
has increased.
Okay.
As the size of the configuration space has increased.
Okay.
So we will stick to Markovian dynamics, whether the system is in equilibrium or non-equilibrium. Dynamics does not necessarily mean out of equilibrium. So if a system is defined through dynamics or through Hamiltonian, we will discuss only Markovian dynamics. So there are some questions that come. Firstly, if I define a model through dynamics, how do I define the dynamics? So I need a proper definition before I can ask the question about how can I simulate on a computer. Then there is a specific question. I was interested in Ising model at a particular Hamiltonian. What dynamics will generate equilibrium configurations? These are the three questions we would like to answer. So defining a model. So what should be given to me so that I can answer the question about the model? So firstly, you have to tell me what are the possible configurations a system can be in, C1, C2, C3, C4. Then you need to tell me how the system evolves in time. And the evolution is given by something called transition rates, which says that what is the rate of going from Ci to Cj. If I give you a configuration C1, Ci and Cj, I will call this transition rates as WCi to Cj. Okay. So some example is given here. I have 5 states and these arrows says there is a W of going from C5 to C1, C1 to C2 and so on. If I give you this much information, I will say the definition is complete. Okay. But what did you understand by transition rates?
the rate at which you go from one state to the other. Like
Yeah, but what does the rate mean?
probability of going from one state. Very
Okay, so it is sometimes I find that this definition of rates creates confusion in students, or not least students in general. So let me spend a bit of time defining precisely what is the meaning of transition rate.
Transition rate could be different from transition probability.
Yeah, so a transition rate, I can say there's a rate of 100 from going from one to another. So it is not a probability as such. So what is the probability? So what does rate mean? So let me take one particular example where let's say radioactive decay. So a atom, a nucleus decays at rate lambda. That's an event. Suppose an event occurs at rate lambda. So this is what I'll call as transition rate, or generally rate. Then the precise meaning is, if I take a small time dt, then the probability of that event occurring is lambda dt. Okay, so this is the definition of. So when anybody tells rate, this should be the meaning of that that the probability of that event occurring in time dt is lambda dt, and when dt is very small, this is much smaller than 1. So this is a well defined probability. Lambda can be any value. It can be, so rate can be any value, positive value, but lambda dt is a probability. Okay, so now, so this is a definition in infinitesimal time evolution. Given that definition, let me ask you, what is the problem? So now there is some radioactive decay going on, and I am waiting, nothing is happening. I ask, what's the probability of that event occurring for the first time at time t? So given this definition for infinitesimal time, is it possible to give the answer for the event occurring for the first time at time t? Yes?
It should not happen before time t.
Yeah. So how it should not happen before time t and occur. So how does one calculate that probability given this definition? So I take an interval from, is everybody following? So I take the interval from 0 to t. I break it up into a lot of dt's, small intervals. Then what's our condition? In no interval should the event occur, and at this final time the event should occur. Okay. So what is the probability? The probability of event not occurring here is 1 minus lambda dt, because the probability of event occurring is lambda dt. That to the power, how many dt's are there? That is t by dt. And then in the final dt it should occur, so lambda dt. Okay, so that is the probability that the system waits for time t and then an event occurs. But that is, it is easy to come in, and we want to take the limit dt is some arbitrary time we have introduced. We want to take the limit dt going to 0. So 1 minus lambda dt is roughly e to the minus lambda dt. So this dt will vanish. So we are left with no dt in the end, and that is that. So it says the probability that the system waits for time t before an event occurs is exponentially distributed. So sometimes, so this is also sometimes the word is used, waiting time. What is the probability of the waiting time? It is e to exponentially distributed. Okay, and this lambda has units 1 by time. So sometimes when people talk about rates, they'll say, oh, it's exponentially distributed. So that is in finite time, and this is infinitesimal time. These two definitions are completely equivalent, but one should not mix up the two. Okay. So to summarize, so you can define rates in infinitesimal time or in finite waiting time. So if I were to do a simulation, I want to do radioactive decay, I can either go dt like this, or I can make jumps like that. So I say I know the first waiting time is here, so I increment time up to here, make one atom go away, nucleus go away, then I can jump up to here, jump up to here. So both simulations or both evolutions are equivalent. Okay, that's the difference between. Okay, clear? Now slight deviation on a computer, how does one generate probabilities? What is the meaning of? So, if you use some basic language, Python, C, I don't know Python either, but at least C and Fortran and so on, what is given to you is a random number generator in 0, 1. So, if I say generate a number between 0 and 1, it gives a random number if you use a good random number generator. More advanced, more higher level languages like Mathematica, MATLAB, you can generate an exponential distribution or generate a Poisson distribution. I don't know, some of them, some known things it can. But it is good to know how to generate an arbitrary distribution from knowing a uniform distribution in 0. This is a uniform distribution. Okay. So, firstly, given a uniform distribution 0, 1, how does one decide that an event occurs with probability lambda dt? So, what you do in the computer, you draw a random number between 0 and 1. You ask, is this number less than lambda dt? Then you make the event occur. If it is greater than lambda dt, nothing happens. Is that clear? Now, what about a distribution like exponential distribution? You are only given a random number generator, but you want to generate a distribution like this. Okay. So, this question is important because sometimes you have funny distributions that come in. So, this answer to this question depends on just this. If I give you the distribution for some variable x, which is px of x, probability distribution, and y is a function of x. So, let us say I know probability of x is a Gaussian. Now I want to know what is the probability of x to the power 10. Okay. Suppose y of x to the power 10. Then I can ask what is the probability for y. If I know the answer for this question, I can answer this particular question, a specific question like this. Okay. How does one change variable in a probability distribution? People, does anyone know? Yeah, if something is true for multivariable, I am sure it is true for single variable also. That is true. So, how does one change variable? So, let me just go through that. So, you are given a distribution for x. I have made the subscript x to make a differentiation between y and x. Okay, there is a distribution like this, and there is some unknown distribution for y. Now, I ask what is the probability that something lies between x and x plus dx. That is this area here. Okay. Now, this x gets mapped onto some y using this y of x. So, it gets mapped here, and this area gets mapped onto some area here. Okay. But whatever, when something occurs here, something must occur here. So, probability must be conserved. Therefore, there is always a relation that p of x dx is p of y dy.
What is the mapping?
You want to know y is some function of x, some given function of x. So, whenever I give you x, I know where y is going to be. But whatever is the probability under this curve must be equal because it is just a mapping of probability. So, this statement is a conservation map, is a statement of conservation of probability.
I should know that function.
That is given to you. Suppose it is given to you, you can always change variables using this relation. Okay. So, that is how you change variables in a probability given in probability. Okay. So, now with this much information, we can ask how do I generate an exponential distribution given a uniform distribution 0, 1. Okay. So, now what you want is, now the reverse question, you are given px of x, you are given py of y, which is this one, but you want to know what is y of x. Previously, I gave the example of I know y of x, then I know how to compute py of y. Now, the question has been reversed. Clear? No.
I don't know the function.
You do not know the function. So, what is my aim? In my aim is I know a random number generator between 0 and 1. But remember my exponential waiting time, my waiting time is exponential. But I want to know how to generate that exponential waiting time. So that's my motivation. So I want to generate some number y, which is distributed like this. But I have only information about 0, 1. So now I want to know. So in my computer, I will generate a number between 0 and 1. Then I have to do this y of x to generate y. But I do not know what the y of x is. That is the question we are going to answer. So we go back to p of x dx is equal to p of y dy. But p of x is 1. It's a uniform distribution. P of y is lambda e to minus y dy. But this is easily integrable. So I say I go from 0 to x, and this goes from 0 to y. I do this integration and I get a relation between y and x. So if I draw a random number 0.1, then my y is 1 by lambda log 1 minus 0.9. Yeah, and you can check that it maps rightly. When x is 0, y is 0. When x is 1, y is infinity. So that 0 to 1 is mapped from 0 to infinity, and the waiting times go from 0 to infinity. Okay.
Basically, the inverse of this. It's basically the inverse. F inverse of.
F inverse. It's basically F inverse. But even if you cannot find F inverse, so suppose I give you a different function here. I give you want to generate a Lorentzian distribution. Then all you have to find out is whether this can be integrated once. So this becomes a Lorentzian. I have to integrate that. You get some complicated function of y. You may not be able to invert y and x, but you can always generate a. So let's say I want to generate 10 to the power 8 Lorentzians. Then on MATLAB or Mathematica, I go and use this formula. I generate x and use some numerical find root or some solution for y as a function of x. I generate these numbers and store them and just use them. Okay. So you say so if you come across some unseen distribution you want to generate, don't get perturbed. There's always a method. That is this one. So I forgot this minus sign is there because this when I solved for this I was careful. There's a minus 1 by lambda. Because this comes this side 1 minus x logarithm and minus 1 by lambda. Okay.
So px dx is equal to px of x equal to py of y. Student report only if it's 1.
Yeah. So if there are always more complications. If the mapping is not 1 to 1, then you have to just be careful and there is a corresponding way of doing that. So you just use your common sense. Probability should be conserved, so use your common sense and do. Sometimes with the function symmetric, you have to put a factor half somewhere. True, that is true. Okay, so now we have discussed rates, how to generate random numbers distributions on a computer depending on the distribution you want. Okay, so now we come back to Markov process. So so what have you been given? You have been given the configurations and the transition rates from configuration to configuration. But we want to now ask, we want a description of the stochastic system. Okay, that is a definition. But now all the configurations are now changing probabilistically because from each configuration there are multiple configurations you can go to and they're going with some probability. So clearly there is no particular trajectory to be predicted. So what we can try to look at is what is the probability, answer the question, what is the probability that the particle or the system is in configuration C at time t. This is the quantity that completely describes the system. Okay. So of course this will not be answerable, but this particular quantity captures the maximum information about the system. So what is P of Ct? So we are now going to ask what is the probability the system is in configuration, given the dynamics, is in configuration C at time t. It will depend on the initial conditions clearly because and it will also depend on the evolution rules. So the evolution is described by something called master equation. This name is familiar to some people, master equation. Yeah. I don't know why, actually I don't know why it is called master equation. Why is it called master equation? It is not master who made it, but for, for some reason it's called, I have not understood, but there's a master equation. It is a very simple enumeration. Uh, the equation is very commonsensical. It says, what is the probability that if the system is in configuration I at time t, how does this probability change with time? So, now if I look at, so one way to imagine this is I have a huge number of different copies of the system. So, in certain fraction of them you are in configuration Ci. Okay, so, the ratio is probability. Now, when I evolve the system by dt, some of them will go out of Ci, but some of them will come into Ci from some other configurations. It was not originally in Ci, but from some other Cj it may come in. Okay. If it comes in, the probability increases. If it goes out, probability decreases. So, this particular thing says what is the way it increases? It is the rate of coming from Cj, j not equal to I with the probability that it was in Cj at time t. Okay. And then there is a loss term, which is I was in configuration Ci, then I go to some other configuration j, and this P of Ci says what is the probability I was in Ci at time t. Okay. So, you do not have to remember this equation, this can be just written down by inspection. After some time it just becomes ingrained. So, this is the known as the master equation, and it completely describes the evolution of this probabilities, which is the quantity we are interested in. Okay.
Why is the summation only was J in the second part?
Because j means I, actually I should put j not equal to I. It says from I can go to many other j. This j is not this dummy indices. So, this j and this j are not the same. This is j prime as we call it. But including, but we have no rate of going from I to I. That is 0. Meaning that rate is 0. We are already in I. So, but technically you should write j not equal to I and j not equal to I. Okay. So, now what is our aim? So, now we want to make some general statements about Markov processes, so that we know what all Markov processes do before going to specific systems. So, I will do some so let me now write down. So, there was a P of the master equation I wrote was for a particular configuration Ci. I write this in matrix form. So, d by dt of P of C1 is W2 to 1, that is the term into PC2 plus W31 into PC3 plus I was in PC4 and I go from 4 to 1, right. This was the whatever I wrote earlier, I am writing in the matrix form, and then there is a negative term, rate of going from 1 to 2 into P of C1 minus 1 to 3 P of C1. Is it clear, this one? This is exactly the same equation as before. I have just written for a 4-state system with the explicit things written down. So, if I look at this matrix, wherever the diagonal terms are negative and the non-diagonal terms are not negative, rates are 0 or positive. So, when I write like this, I can write in matrix form where P is a column vector and W is a n cross n, which is the matrix of this kind, WP. And what are the so, if I write an equation dP by dt equal Wp and give you a matrix W, when can you say it is a Markov process? W should satisfy some properties. What are those properties? We will just generalize from what we saw here. Properties are that Wij should be greater than or equal to 0 when I is not equal to j. Non-diagonal terms are positive, non-negative. The diagonal terms are negative. And if you look, if I sum each column W21, 23, 24 cancels out exactly with this one, right. Each column when I sum, it is exactly 0. So, Wij, j is my column sum. So, when I sum over I, it is 0. So, if I give you, so now forget about the even telling in words or person meeting A, B, B, I can just give you a matrix with these properties that will constitute what we want to call as a Markov process.
How did you come up with W like what did you write?
Yeah, this what I wrote is just the. So here, if I write P C1 by I put I equal to 1, d by dt of P of C1, it says it is W C2 to C1, C3 to C1, C4 to C1. And here the negative term, it is C1 to C2, C1 to C3, C1 to C4. So that particular thing I have just written down explicitly in this form. Okay. Okay.
Quantum sum being zero implies like you are summing over all the rates from going from state I to j and sum over all the i's, and that being zero, like I cannot get an intuition of that.
Yeah, but because your WII is not, it doesn't follow the definition.
Oh, acha, okay. This
Your
is
statement of going from I to j.
okay.
So WII is a negative number. That particular statement fails that.
Okay.
Okay, so the first point. So now I have given you a matrix like that. So we are going to find some general properties of those matrices. So this was my master equation, dpi by d. Now I write for a particular component. Dpi by dt is wij pj sum over all j now, not j equal, just not j equal to, not equal to I. J equal to I also is involved in that. Okay. Now suppose I take this equation and sum over all I. So what am I doing? I am doing in this row vector. What is the meaning of that? Sorry. So what am I doing? I am summing over, when I sum over I am doing P of C1 plus P of C2 plus P of C3 plus, I am summing over this column, row. Okay, that is what I am doing. So this summation over I goes this side, summation over ij, wij, p. This is just matrix product. Okay. But now I can interchange I and j. So what was I, what was j? I become j and I. Now when I do the sum over I, it is the column sum of w, right? The what we did earlier column. And this j, this pj does not matter. I can make this pj come this side, and the column sum is 0. So therefore, the right hand side is 0, precisely that. And therefore, when I do the sum over P1 plus P2 plus P3, P of C1 plus P of C2 plus P of C3, that probability, that sum does not change with time. And therefore, it is equal to 1. Why is it equal to 1? Initially, I give you a configuration, which is, I have to tell you what's the probability of the system being in configuration 1, 2, 3, 4, 5. But it's a probability, it has been some configuration, so the sum must be 1. Then it remains that this remains 1 forever. So this is a well defined probability, that is the point. Okay. So this column sum being 0 is responsible for probability being conserved. So that is the key point. Okay, clear?
So can you just explain the second last step?
The second last step. This one? Yeah. So there was a sum over I, sum over j. And now I interchange the sum. I can do the sum over I first. But since P is this is Pj, I can make this Pj come this side. And now when I do sum over I, Wij, it is a column sum of W, which is 0 for any j, any jth column.
Shouldn't this be true when we are writing in terms of probability, that the probability of exceeding any of the states should add up to 1?
Should add up to 1. So if the W matrix satisfies this property, it will definitely satisfy. So the column sum has to be 0. That is the point. Now, this equation looks like your Schrodinger equation. Right? But what is the difference? Difference is W need not be Hermitian. Your quantum mechanics, your Hamiltonian is always Hermitian. But here, it need not be Hermitian. Why? Because Wij, the rate of going from I to j, need not be the rate of going from j to I. I can say, I can give, a particle can give birth to 2 particles, but 2 particles cannot join and become 1 particle. So it immediately breaks this, not true in general. I can always make a model where it is equal. If it is equal, it becomes Hermitian. Okay. Now, in quantum mechanics, when you get a Hamiltonian, what do? You run around immediately finding eigenvectors and eigenvalues, right? So, here also we will be interested in finding out eigenvectors and eigenvalues of this matrix W, okay, transition matrix or W matrix. But it is very important to remember that if a matrix is not Hermitian, your left and right eigenvectors, there are many things you assume when you take a Hamiltonian, you find eigenvalue, then you find the right eigenvector or eigenvector, because right and left you do not distinguish, they are both the same. But when the matrix is not Hermitian, left and right eigenvectors need not be the same. Okay, that is an important point. Okay. So, now can we say something more about eigenvectors and eigenvalues? Now, my claim is 1 1 1 1 1 is a left eigenvector of W. Why? Column sum is 0. So, if when I from the left, when I multiply any column, 1 1 1 1 into any column is sum of the column vectors, but the sum of the column is 0. So, therefore, we can make a bigger, more specific statement, 1 1 1 times any column is 0, because column sum is 0. Therefore, not only is 1 1 1 is a left eigenvector, is a left eigenvector with 0 eigenvalue. Okay. So, now we have identified two properties, that there is an eigenvalue 0 and 1 1 1 is a left eigenvector. So, see, these are some specific importance. Now, the right eigenvector you do not know, right eigenvector is not 1 1 1 transpose, it is not that. So, we will call it PS of C. Just to make in some notation, I will call it as probability of C with a subscript S. Okay. Now, what are the other properties of W matrix? Other properties we are just going to state. You can look in some of the things are some math result, some of them are not. But these are properties that are true for any W matrix. First one is this eigenvector eigenvalue 0, it is non-degenerate, means only one eigenvalue is 0, you cannot have two eigenvalues 0. Okay, that is an important point. It also says all entries of this right eigenvector of 0 must be positive, non-negative. Actually, must be of the same sign, which will take to be non-negative. Okay. These are just statements you have to take for that this is true for any Markov process. The third statement is I have how many, if I have an n cross n matrix, how many eigenvalues are there? At most n? Why at most n? Yeah, it is exactly n. No, okay. So there are exactly n eigenvectors. The statement is that all the other eigenvalues, lambda 2, lambda 3, lambda 4, they may be complex, but the real part has to be less than 0. This is also true if I give you those W matrix like that. Okay. And finally, eigenvectors are orthogonal, like usual Hermitian things, eigenvectors are orthogonal to each other. So let's forget about those details. You see, in quantum mechanics, also make that not, if they are not, how do you, if suppose two eigenvalues are there and they have two eigenvectors, you can always go there and do an orthogonalization of that subspace. So those details you can always say can be taken care of. But so we have not specified any specific model. All these properties are true for any Markov process. Okay, any dynamics you give, this is true. Any question? Okay. Now, why did we do these eigenvectors, eigenvalues, and so on? So we will again follow what we learned from quantum mechanics. In quantum mechanics, we do eigenvalues, then we take some arbitrary wave function, expand in terms of the eigenvectors. So here also we do the same. So we say this is what is the probability of being in configuration C at time t? this vector, this row column vector, I will expand in terms of eigenvectors of W. So there is, so P of Ct, there is some contribution from the lowest eigenvector. Psi 1 is eigenvalue 0. There is some prefactor here, A2t, A3t, and so on. This is general expansion. Now I want to determine what is A1, what is A2, what is A. All this will follow exactly like in quantum mechanics. First statement is, suppose I take an inner product with 1, 1, 1, 1, 1, which is our left eigenvector of the eigenvalue 0. Now, it is orthogonal to all psi 2, psi 3, psi 4, psi n. So, all those terms will go to 0. So, you will get A1 of t, because this is 1, 1, 1 into psi 1 is 1. So, all you are left with is A1. But what is the LHS? LHS is sum of the columns of PC1, which we already showed is independent of time. It is 1. So, LHS is 1, right. This is the sum of the probabilities of all the configurations, and RHS is A1 of t. So, A1 of t is always 1. It does not depend on time. So, I cannot choose an initial condition in which A1 of t is 0 different from 1. Whatever vector I give, if I take a cross product with psi 1, I get 1. That is something that is not in quantum mechanics. You can choose, okay, I will choose something only with psi 3. Not possible here. You have to choose A1 equal to 1. Okay.
So get psi 1 is 1, 1, 1.
Get psi 1? Yes. Get psi 1? The psi 1 we do not know, but its left counterpart is 1, 1, 1, 1. So, in the where we previously in quantum mechanics it was psi 1, psi 1, but now it is psi 1 L, psi 1 R. That is the inner product.
So the LHS is 1 because the sum of probabilities is
1.
That's why.
Yes. Sum of that which we showed earlier, that the sum of probabilities is 1.
Sir, is psi 2 a function of time?
No, psi 2 cannot be a function of time because the W matrix itself has no time. It's only rate. So, the eigenvectors are also independent of time. Did I write? Oh, I am sorry. That is not a function of time. That was just an error in the thing. Okay. So, this much we could show.
But psi 1, psi 2 all are the
Eigenvectors of W.
eigenvectors which span space.
Yeah. So, there are some eigenvectors. Yes.
So what is happening to RHS, like when you multiply 1?
1, 1, 1.
Yeah, this side.
So, what the eigenvector corresponding to eigenvalue 0 is orthogonal to all the other eigenvectors. So, when I do 1, 1, 1 into psi 2, it is 0.
And it's not orthogonal to psi.
It is orthogonal to psi 4, psi 1. You cannot, psi 2 bar psi 1, you cannot say anything. But there's a nice statement here also, no? All the other eigenvectors, the column sum must add to 0. That also is a statement you can make, because 1, 1, 1 into psi 2 is 0, 1, 1, 1 into psi 3 is 0. So, all the other eigenvectors when I add, it must add up to 0. So, that's another statement you can make about the W matrix. Okay. Now, we go back to master equation. So, remember the master equation was d by dt of P of Ct on the left hand side. For P of Ct, I am going to substitute. Are people following? If somebody, most people are following. Okay. So, so now I take this expression for probability of being in configuration C and take the derivative of that. So, the left hand side becomes dA1 by dt, dA2 by dt, and so on. Right hand side, remember, is W times P. dP by dt was WP. So, it's W times psi 1 plus W times psi 2 and so on. Okay, so, what have I done? I have taken the master equation dP by dt is WP, substitute for P in terms of this eigenvalue expansion. So, the RHS is W times psi 1 is what? Psi 1 is eigenvector of W. So, it is just lambda 1 times psi 1, but lambda 1 is 0. So, this should be 0. W times psi 2 is lambda 2 times psi 2 and so on. So, next term is lambda 3 times A3t, lambda 4 times A44 and so on. So, now
I one term should not come.
psi 1 term should not come. I was careless, so it is just that. It's-
Zero for left eigenvector for right.
no, W acting on psi 1 is lambda 1 times psi 1. Whether W acting on the left eigenvector is also lambda 1 times left eigenvector. So, lambda 1 I forgot to put, lambda 1 is 0. So, there should be lambda 1 here, which is 0. No, that was an error. So, now you have an equation. Now, I want to find what is my aim. I want to find out how does A2 behave, A3 behave and A4 behave. So, to find the behavior of A2, I take an inner product with the left eigenvector of psi 2. Okay. So, when I take the left eigenvector, this becomes 0. Here it becomes dA2 by dt. And the right hand side, this is 0. Here I get lambda A2, lambda 2 A2.
Is that psi 2 square?
No, psi 2 left, the left eigenvector of psi 2. So, therefore, I can solve for what is A2 if I know the initial condition. A2 of 0 is e to the power lambda 2t. Like that, if I do A3, A3 of 0 e to the power lambda 3t. Okay. But this A2 of 0 is just fixed by the initial condition. There. So now I have solved for all the coefficients in terms of the eigenvalues of W. Okay. So now I plug it back into my expression for probability of C, which is A1 of t, which I put 1 into psi 1 plus A2 of 0, this is A2 of t and this is A3 of t and so on. And but remember that the real part of lambda 2, real part of lambda 3, real part of lambda 4 all are negative. Now we want to ask, I give you such a system and I take the limit t going to infinity. I run the system evolves and I look at very large time. When I look at very large time, all these terms go to 0 because they are all negative. Okay. So, what is remaining? It is only psi 1, which I called as Ps of C. The notation for psi 1 was something of Ps of C. So, when I do the evolution for long time, independent of what's the initial condition, I always go to some state which is the ground state of W matrix, which is called the steady state. So, the technical word is that in the long time behavior, I always go to a unique state. State, not the state, the probabilities go to a unique probability. The configuration keeps changing and that state is called the steady state.
You mean the distribution goes to 0?
The distribution goes to a invariant state, which is the steady state, and that happens to be the right eigenvector of W matrix with eigenvalue 0.
What is PS?
That is the psi 1. In this one, because this is A1 of t into psi 1, A1 of t we have decided is always 1, independent of initial condition. Or A1 of 0 is 1. Okay. Now, there is some small, so this statement is important. So, when you do a Markov process, you are guaranteed a steady state which is unique, okay, and it is non-degenerate. There are some specific conditions that you have to, this is true if system is some word ergodic is there. It means that suppose I say that 1, 2 and 3 states only interact with each other and 4, 5 and 6 only interact with each other, then you can be either stuck in 4, 5, 6 or 1, 2, 3. So, it becomes not. So, ergodic means you should be able to go from any state to any other state using the dynamics. Okay. So, these statements are true for some such thing. So, now many of the problems you will do are involve Markov states, Markov processes, and you must know what are the generic properties of them. Okay.
How did we get the second part, like?
Eigenvector 0?
No, in the expression like PCT minus.
Ah, okay. So, now usually, at least when if I were to do some dynamic process, there are two things that interest me. One is what is the long time behavior, which is the time invariant steady state. The other is how do we approach the steady state. Okay. So when you are not at t equal infinity, but very far, very large t, then you keep the first term. So which is the first eigenvector, which is slightly closest to 0, and that determines how you approach the steady state. Okay. And sometimes you can theoretically find out lambda 2, sometimes you cannot, you have to do it numerically and so on.
These lambdas are in descending order.
Yeah, okay, that, yeah, I ordered them in a in modulus wise. Okay.
So that last statement.
Ah.
So if I let's say start with some so in this way of analysis, where we get reflected that at some what point we realize that this is not important.
That no, if you simulate the system with different initial conditions,
This particular way.
you have to say, suppose I give you some dynamics, and I at least let me give you an example of what I know. Suppose I want to show that some dynamics is ergodic. Then I have to sort of show that I should be able to go from A to B. If I manage to show that I can go from A to some standard state, B to some standard state, then I can reverse A, B and so on. You have to show, otherwise sometimes there are obvious non-ergodic behavior. No? When you look at the W, okay, if I write down the W matrix and it does not break up into blocks, then it is ergodic. If it is blocks means,
We can always check that.
if it breaks blocks means that it becomes, there is a block here. You can reorder after reordering. Then there is a block here. Rest are 0. Then if I start the system here, I'll keep remaining here. If I start the system in this configuration, I'll remain here and here. So then you don't know. So there are 3 different steady states for this, and you cannot say. So the properties will break down. So usually it is not the case, but if you have to be careful. You have to keep it back of the mind that, oh, this assumption of ergodicity is true. Okay. Now, yeah. So determining the steady state. Now, given a W matrix, I do not know what my steady state is a priori, but that is what it makes it interesting. So if you are looking at some system, what you look and find is some dynamics. Then determining steady state becomes the key. And sometimes when you do the simulation or you do the analysis, you will find some unexpected results. Okay. So the and the second is the what I state. So these are 2 questions, and then the spatial patterns they form and things like that become important. Okay. So this was a very fast primer to Markov processes, and now how to simulate a Markov process. I already told you how to generate random numbers, waiting times and so on. So there is nothing more you can do beyond that. If you so often you are faced with, at any point of time, there are multiple events possible, because you are in configuration Cj, you can go to 10 configurations, and all of them at different probabilities, rates. You can do the simulation infinitesimal time or do in finite time. There are, as far as I know, there are no generic speed up routines. You have to be clever to look at the problem. Sometimes if you stare long enough, you realize that, oh, I can make it much faster than just doing brute force definition of rates and probabilities. But those are problem specific.
By finite time, you mean discrete time?
Yeah, that each one waits for a long time. I have 100 events, but each event I know what is my lambda prime. So I know I draw a number from the exponential waiting time. I have 100 waiting times. Then I find the minimum of them. Then I go to that. Then I again do this analysis and do. Okay. But you can have some straightforward generalized speed up routines. So suppose I have n possibilities with rate lambda 1, lambda 2, lambda 3, lambda n meaning at each time I have n possible transition that can happen. Now, what's the total probability? Is lambda 1 plus lambda 2 in a small time dt. Total probability of any of these events happening is lambda 1 plus lambda 2 is lambda n dt. Okay. Now, I don't want to make dt so small that nothing happens in that dt. So, I want to make the program rejection free. So, I will choose my dt so that it is large enough so that an event always occurs. So, I can to do that I can say that the probability of some event occurring is exactly 1. That fixes for you dt given the lambda I. Then once I know dt, I ask what is the probability the ith event occurs, that is lambda I by lambda 1 plus lambda 2 lambda. Okay. So, this is the standard procedure one might use. And so, how does one find out which event I to occur? You take a random number between 0 and sum over lambda I, and then this whole stretch is broken up into lambda 1, lambda 2, lambda 3 and so on, these segments. I draw a random number between 0 and lambda I, this red point. I throw the red point somewhere, red point lies here. I choose a third event. Okay, so that is the thing. I choose my third event, program goes forward by that dt. Then sometimes once it goes forward, my lambda i's will change. Then dt might change. So, I will go from one dt, next dt might be here, next dt might be here, like. So, my program goes forward like that. Okay, that is, and one need not even worry if dt is large. In my experience, if dt is not so small, also things work quite well.
Can you go over this example?
This one. So I'm saying that at some point in time, I have possibility of n events can happen. So so I'm confident Ci, I can go to 100 things. There are 100 rates of that happening. That I'm calling as lambda 1 to lambda n. Now each one occurs with probability lambda 1 dt, lambda 2 dt and so on. So the total probability of some event occurring in time dt is sum over I lambda I dt. That is this sum. Now if I make dt very small, then nothing will happen. But I want to optimize. If I make dt too large, then it will become not a probability. So I will choose an optimum dt where the sum is 1. So then once I do that, then I have to ask what is the probability that the ith event occurs. So that is just the ratio of that rate to the total rate. And now I have to pick up how do I pick up that? I choose a random number between 0 and the denominator. That lies somewhere on this line. But that line I have broken up into lambda 1, next one is lambda 1 plus lambda 2, lambda 1 plus lambda 2 plus lambda 3. If it lies in this segment, I will call it lambda 3. I will choose event 3. So now, of course, this searching is difficult. So you can be clever in trying to find out where does this point lie in fast ways. That is up to you. If you can make some scheme of how to identify the reaction in a fast manner.
This is Gillespie algorithm.
No, so I don't know why it is called Gillespie algorithm. This is just Monte Carlo simulation. In some context, the waiting time comes, people call it Gillespie algorithm in some parts of chemistry or something, but there is no need to give a name for this. This is just standard Monte Carlo simulation.
So this method relies on finding out the eigenvalues for
No. Those were generic statements. This is, I don't even know W matrix, nothing. I am only given the dynamics, I am simulating that.
You have been given a master equation.
Not even a master equation. You have just been told, I have this agents going around and they have some reaction.
And the transition probability.
Yes, I have just.
Definitely lambda was
Oh, this lambda is not eigen. This lambda is the rates. Oh, I am sorry. This I didn't say lambda sometime. Oh, this lambda is not the other lambda.
These are not eigenvalues.
These are just rates lambda 1, lambda 2, lambda 3.
What does rejection mean?
Rejection means if I choose dt too small, then the probability of an event occurring is lambda 2, lambda 3 is 0.5. So half the time I will not have an event, the system will remain the same configuration. But I want to speed it up, then I will wait one more time to do that. So I can make it rejection free in that manner. Okay. The other way to do it is, of course, the finite waiting time updates. So now I have again n events. I have waiting times for all of them. But now I have to decide which is the shortest waiting time. So this sort of simulation depends on how to sort these waiting times and how to keep them sorted. That part has a lot of overheads, but sometimes efficiency can be gained by tricks. You know, how do you sort things fast and this one, that is up to you. So sometimes the problems are where some waiting times don't change. So then you can keep them sorted and find out where exactly to put and so on. And the other thing is parallelization. These Markov processes, you know, the evolution itself we cannot parallelize because only one event occurs at a certain time. But the searching and sorting, all these things, parallelization helps. Okay, so and the simplest parallelization is something I'm throwing a name. There is something called OpenMP parallelization schemes. I don't know, multiple. Just some, if you have are faced by how to parallelize. So the simplest parallelization is something called OpenMP. Okay, so that is some word to remember. Okay, that is now with this, I'll stop here because my time is up. Now, so what did we do today? So we said that if I define a model where the model is given and the dynamics is given, what are the generic properties such systems obey? There's a steady state, there's a unique steady state, and you have to just wait long enough to reach that state. Then how to simulate such a system also we discussed. Okay, so all this talk up to now was about Markov process, but yesterday we talked about no dynamics. We talked only about energies. So no dynamics specified. How does it apply to equilibrium systems? Okay, all these talks. So one last slide. So now the question is reversed. In equilibrium dynamics, what is given is the probability of a configuration, e to the power minus beta e. And the question being asked is, what dynamics should I give so that my steady state is this? So previously I was asking, if I give a dynamics, what is my steady state? Now my question is, given the steady state, what dynamics should I give? So the clever, so now I have lot of freedom in choosing a clever dynamics to reach it. I can choose fast dynamics, slow dynamics, that is up to you. So this is what we will discuss next time. Is the correct time? Yes, stop. Any yes.
Markov process through like the Schrodinger approach, right? So, but we know in QM there is also like a Heisenberg picture to things. So, if I could, so let's say I have this system, instead of writing like a Schrodinger evolution equation, could I equivalently look at it through a Heisenberg, and that would correspond to some other physical way of looking at this Markov process?
I got it. I can show the inside.
Actually, I do not know the answer to that specific question. That statement that
Like the rate itself evolves instead of the state. The rate matrix evolves.
Yeah. So whether that is useful or not, I do not know. I do not know the answer. But the point of this statement was that, you know, using that thing, we could derive some properties of Markov process, which is generic. But I do not know the answer to that particular question. But some of the other techniques from quantum mechanics, like path integral approach, things like that, are sometimes useful for solving this equation. But your specific question, I do not know the answer. Any other? Somebody was asking about memory simulations. Memory simulations, you have to just, if it's, as I said, finite time simulations. If I have infinite memory, these results don't hold. But simulations, the same technique. There's a rate. That rate depends on your past history. But if the simulated model with rate, I use the same waiting time distribution or whatever distribution that comes. Sometimes if you integrate over the memory, the distributions might change. It's no longer exponential. It can be something other distribution.